You don't need giant models to succeed with AI. Executive summary. Smaller language models scale from 1 billion to 70 billion parameters, offering trade-offs between capability and efficiency. 70B models provide state-of-the-art reasoning and knowledge, but demand immense compute and energy. 7B models balance strong performance with practicality, making them versatile for many applications. 3B models emphasize speed and accessibility, suiting individuals and smaller teams, but with limited sophistication. 1B models are lightweight and energy efficient, ideal for narrow or embedded tasks, but lack depth and reliability. Notice that these models are much smaller than the trillion-parameter models that companies like OpenAI run. Article language models have rapidly advanced in recent years, and one of the most significant axes of development has been scale. The number of parameters, roughly the tunable weights inside a model, has grown from millions to billions, and even hundreds of billions. Each increase in size brings improvements in performance, but also raises new challenges in terms of efficiency, cost, and accessibility. In this essay, we will examine the advantages and disadvantages of 4 different model scales: 70 billion, 7 billion, 3 billion, and 1 billion parameters. By comparing these tiers, we can better understand the trade-offs between capability and usability, and how different scales may serve distinct roles in research, industry, and society. 1. 70 billion parameter models. Pros. 1. High performance on complex tasks. At 70B, language models begin to approach the state-of-the-art in reasoning, text generation, and multitask learning. They tend to perform exceptionally well on benchmarks such as MMLU, GSM-8K, and coding datasets. Their sheer size allows them to capture long-range dependencies and nuanced relationships in language, enabling outputs that are both sophisticated and contextually appropriate. 2. Few-shot and zero-shot generalization. Larger models exhibit strong emergent behaviors. They can solve problems with little or no task-specific training, such as summarization, translation, or reasoning puzzles. This makes them versatile tools across many applications, from chat assistants to enterprise-level analytics. 3. Knowledge retention. With 70B parameters, models have greater capacity to memorize and represent factual knowledge from training data. They are more likely to recall obscure facts, handle domain-specific jargon, and give detailed explanations than smaller models. 4. Robustness and reliability. Large models tend to produce more fluent and coherent text with fewer grammatical errors. They also handle edge cases better, reducing the need for extensive fine-tuning. Cons. 1. Compute and energy costs. Training a 70B model requires massive clusters of GPUs or TPUs, and inference using the model is expensive as well. Serving such models at scale is resource-intensive, making them less accessible for small companies, startups, or researchers without large budgets. 2. Latency and deployment challenges. Even with optimized inference frameworks, 70B models are slower to respond compared to smaller counterparts. Deploying them in real-time applications, like mobile apps or customer-facing chatbots, is often impractical without substantial infrastructure. 3. Environmental concerns. The energy footprint of training and running large models raises sustainability questions. Each training run can consume megawatt-hours of electricity, contributing to carbon emissions. 4. Risk of overfitting and bias amplification. Larger models can overfit to biases present in their massive training corpora. While scale improves some safety metrics, it also amplifies risks if not carefully aligned. 2.7 billion parameter models. Pros. 1. Balance of performance and efficiency. Models in the 7B range strike a useful middle ground. They are powerful enough to handle many advanced NLP tasks with high accuracy, yet small enough to run on a single high-end GPU. This makes them accessible to researchers, startups, and developers without hyperscale resources. 2. Fine-tuning flexibility. 7B models are large enough to benefit from fine-tuning and instruction training, but small enough that fine-tuning can be done on modest hardware. This is especially appealing for domain-specific applications, e.g., legal, medical, or financial assistance. 3rd, practical for edge use. With optimization such as quantization, 7B models can be deployed on local servers or even some advanced edge devices. This reduces latency, improves privacy, and avoids reliance on centralized cloud services. 4. Sufficient knowledge retention. While not as encyclopedic as 70B models, 7B models still store a substantial amount of world knowledge, making them suitable for applications that require a broad but not exhaustive knowledge base. Cons. 1. Performance ceiling. Although competent, 7B models cannot match the nuanced reasoning or factual coverage of larger models. They may struggle with highly technical tasks, subtle logical reasoning, or creative problem-solving that benefits from scale. 2. Still expensive at scale. While cheaper than 70B, 7B models are still non-trivial to deploy at high volumes. For organizations serving millions of users, even modest latency and compute costs can accumulate. 3. Knowledge gaps. Smaller size means that rare knowledge or very specialized topics may be missing or represented inconsistently. This limits their utility for niche, scientific, or industrial domains. You can compensate for this by using tools such as GPT-4.all that let you add your own data to the knowledge base. 3.3 billion parameter models. Pros. 1. Lightweight and efficient. At 3B, models become significantly more lightweight. They can be run on consumer-grade GPUs and CPUs. This makes them practical for individual developers, hobbyists, and small research teams. 2. Faster inference. The reduced size means faster responses, which is critical in latency-sensitive applications like voice assistants, real-time translation, and chatbots. 3. Lower cost of training and fine-tuning. Fine-tuning a 3B model is affordable for many small teams. This encourages experimentation and customization, broadening access to tailored language AI solutions. 4. Privacy-friendly deployment. Because 3B models can run locally, they can be used in sensitive environments where data privacy is crucial, e.g., healthcare, finance, or government. Cons. 1. Reduced accuracy and reasoning. While still useful, 3B models often fail on complex multi-step reasoning, nuanced writing, or factual recall. Their outputs may be less reliable, requiring closer human oversight. 2. Limited contextual understanding. Smaller models often struggle with very long contexts, documents, conversations, or code bases. This makes them less suitable for tasks like long-form summarization or analyzing extensive datasets. 3. Risk of simplistic outputs. Responses from 3B models can be generic, repetitive, or shallow compared to larger models. This diminishes their usefulness in professional-grade applications. My favorite test question is, tell about Nikola Tesla. 3B models do just as well as 7B models on this test. 4. Competitiveness in industry. As 7B and larger models become more common, 3B models may be seen as underpowered for commercial use, relegating them mainly to educational or experimental purposes. 4. 1 billion parameter models. Pros. 1. Highly accessible. At this scale, models can run on CPUs or small GPUs, and even on some mobile devices with optimization. This democratizes access, enabling widespread experimentation and low-cost deployment. These work very well if you build a custom database for them. 2. Ultra-fast inference. With fewer parameters to process, 1B models can deliver near-instant responses. This makes them appealing for embedded applications, such as smart appliances, robotics, or offline tools. 3. Minimal resource requirements. Training or fine-tuning a 1B model can be done with relatively little compute, allowing academic labs, students, and hobbyists to engage with cutting-edge AI without prohibitive costs. 4. Energy efficiency. Because they require far less computation, 1B models are more sustainable to operate. This makes them suitable for environmentally conscious applications. Cons. 1. Severely limited capabilities. At this scale, models often lack the ability to perform sophisticated reasoning or generate coherent long-form text. Their utility for advanced NLP tasks is limited. 2. Poor knowledge retention. 1B models cannot encode as much factual knowledge, meaning they frequently produce incorrect or shallow answers to knowledge-intensive queries. 3rd, high risk of hallucination. Small models are more likely to generate incorrect or nonsensical information, requiring extensive guardrails to be usable in production. 4. Narrow use cases. While fine for simple classification, autocomplete, or intent recognition tasks, 1B models are often inadequate for general-purpose AI assistance or professional use. Comparative analysis. When viewed together, these 4 scales form a continuum of trade-offs between capability, cost, and accessibility. 70B models deliver state-of-the-art performance, but at enormous computational cost. They are best for enterprises, research labs, or governments with vast resources. 7B models represent a sweet spot, powerful enough for real-world applications, yet efficient enough for smaller organizations to deploy. 3B models democratize access, offering reasonable performance for individuals, educators, and lightweight enterprise tasks. 1B models prioritize accessibility and efficiency, but their limited intelligence confines them to narrow applications. This scaling law illustrates a critical reality of AI. Bigger isn't always better, and right-sizing a model to its intended use case is essential. Conclusion. The parameter scale of a language model fundamentally shapes its strengths and weaknesses. At 70B parameters, models achieve state-of-the-art performance with deep reasoning and knowledge recall, but are resource-intensive and environmentally costly. 7B models strike a pragmatic balance, offering versatility and strong performance without prohibitive costs. 3B models emphasize efficiency and accessibility, making them valuable for smaller teams and latency-sensitive applications, albeit with reduced sophistication. Finally, 1B models are the most accessible and lightweight, suitable for embedded and low-resource scenarios, but limited in reasoning and reliability. Ultimately, the choice of model scale should depend on the goals, constraints, and values of the user. For high-stakes reasoning or enterprise applications, 70 billion or 7 billion may be justified. For broader accessibility and experimentation, 3B and 1B are more practical. As the field evolves, techniques like quantization, distillation, and retrieval-augmented generation will continue to blur the boundaries between these tiers, enabling both powerful and efficient AI systems to coexist. I've noticed that for a given size, models released in 2025 tend to be faster than models released in 2024. This may be due to improvements in distillation techniques and other ways to improve performance.